The first thing that we really need to talk about to really understand materials and the science behind them is what makes the material itself. And the material we've talked about previously, it's the composition, it's the what atoms you're using, what ions, what molecules you're using, and it also comes down to the atomic arrangement. And the atomic arrangement is how it's connected. How are they bonded together? And so a large part of really understanding things is understanding the bonds. And so we have a couple questions here and what we're going to talk about today. What kinds of bonds are there? You've taken chemistry before, you know the different types of bonds that there are. We're going to do a review on that. We're going to go talk about why they bond that way. And that's kind of our second question here is what dictates the bond type. So what kind of bonds are there and what dictates what type of bond is actually going to happen. All right, so what kind of bonds are there? There's primary bonds and there's secondary bonds. Primary bonds are when the electrons are interacting between atoms. So there's an atom over here on one side, and there's another atom, and they want to interact together. And the way they interact is the electrons are actually interacting between the atoms. We'll show some diagrams of that along the way. Just quick overview right now. Secondary bonds, they are when there's an interaction due to just electrostatic attraction. The individual electrons aren't really doing anything. It's just the fact that there's some positive or negative charge associated with the atom or the molecule, and that is a secondary bond. All right, we have three types of primary bonds. We have ionic bonds, covalent bonds, and metallic. And our secondary bonds are sometimes called our van der Waals forces or van der Waals bonds. I shorten that with a VDW. We have four types of these. We have hydrogen, dipole-dipole, dipole-induced dipole, induced dipole, and induced dipole. And in short, these last two here, number 3 and 4, anything that has an induced dipole are often called London dispersion forces, and they are just very, very weak secondary bonds. All right, we will talk about these throughout the rest of this video, but that was just the overview. All right, so what dictates the bond type? The bond type, first we want to look at the periodic table. We talked about the atom, we talked about the periodic table in a previous video. What periodic table means is it means that as we go through the table, things seem to repeat after a while. So things will act a certain way in each column. So here's the periodic table down here, and it already has some arrows built in about what we're going to talk about. But the things in this first column are going to act a certain way. And in the second column, they act a certain way, and so forth. Which means if we kind of read from left to right the way that we normally read, like a textbook or something, we see that every time that we get to the end of a row, we come back around and we are in a column that we've already been to before, and so we get similar properties. In these columns, we are going to start getting similar electron structure as well. And that is going to get into our valence electrons. And valence electrons are the electrons in the outermost shell. And those are the electrons that are responsible for chemical bonding or primary bonding, where we actually have electron interaction. So what we're going to look at on our periodic table is we're going to look at the property of electronegativity, which often is just written as En for electronegativity. And what this does, it measures the tendency of an atom to attract a pair of bonding electrons. Or in other words, how much does it want electrons compared to another atom? And what we have is I have this picture. I found this on the internet, and it shows that we have these arrows, and the arrows that I really want to talk about, you can look at all these arrows. It would be a good thing to look at them and figure out why does the atomic radius change when we go down and to the left, and why does our ionization energies increase when we go to our right and up. But what we really want to talk about right now is we want to talk about these arrows in the middle that are diagonal. And that is our electronegativity approximately. And so electronegativity tends to increase when we start here at the bottom left and as we go up to the top right. And so these boxes of the periodic table, we don't have the elements written in or anything, but the ones here that are yellow, those are our nonmetals, and our nonmetals have high electronegativity, meaning that they really want to have more electrons. And as we move down the gray ones, and to be honest, a large portion of the periodic table is gray, but the gray elements are our metals, and metals don't really care about gaining more electrons. We have this stair step, and you might have seen this stair step. It might be easier to see on maybe some other periodic tables which have this one's kind of covered up with some arrows. But we have this stair step in the middle called the metalloids, and that stair step is kind of the transition between when something acts more like a metal or a non-metal, or in other words, when it really, really wants to gain more electrons and when it doesn't really want to gain more electrons. And so we have some general rules here. Generally, when the electronegativity is between 0 and 4, and so 2 is approximately the midpoint. And so 4 is our high end. It means that it really wants that bonding pair of electrons. 0 means that it doesn't want it at all. And 2, you could kind of say is neutral. It's not the fact that it could take them or leave them. It just means that it doesn't want them as much as our nonmetals, which want them really, really badly. All right, so I'm going to just quickly go over our 3 types of bonds, and then we're going to talk about them specifically in a little bit more detail. So first, our primary bonds are dictated by the magnitude and difference between the electronegativities of atoms. So what that really means is if I find the electronegativities of 2 atoms, I can see what the difference is between them to tell you what type of bond they will most likely make up. Ionic bonds deal with electron transfer, and that is in quotations. It's not 100% true, but it's a good way to think about it. And these types of bonds are between atoms that have large differences in electronegativities, meaning metals and nonmetals. An example that is often used is sodium chloride, NaCl. And so going back up here to this periodic table, large differences in electronegativities would mean I have something that's a very electronegative up here in our nonmetals. And it would be bonded with something way over here that's not a metal. And when that happens, or when it is a metal, and when that happens, we get an ionic bond. And our sodium is over here on the left, and our chlorine is over here on the right, so we can get an ionic bond when those 2 atoms come together. Covalent bonds, we often say, are electron sharing. They share their electrons. This is between 2 atoms that don't really want to give up their electrons, but they really, really want them. So it's between atoms that have similar electronegativities, and both electronegativities are high. So meaning that both electronegativities are normally greater than 2, and these are going to be your nonmetals. They're going to be when atoms in these yellow regions want to bond with each other. An example would be something like diamond. A diamond is carbon, it is a nonmetal, and so when it bonds to other carbons, it doesn't want to transfer any of its electrons over to the other atom. What it wants to do is it's willing to share them, but it's not willing to give them up. Lastly, metallic bonds, often talked about as a sea of electrons. This is between atoms that have similar electronegativities, but both electronegativities are low, and those would be our metals, these gray boxes that we see. An example would be something like copper. They are low in electronegativity. They don't necessarily want the extra electrons super bad, so they aren't pulling them. They're not trying to transfer electrons. They're not trying to share them as strongly as a covalent bond. They still want their electrons, but they're okay with them just kind of being around, and that's what we mean by the sea of electrons. Again, throughout this video, we will talk a little bit more about what each of these mean. So let's go to ionic bonding. And ionic bonding is going to be, again, electron transfers between atoms with large differences in electronegativity. And it's when an electropositive and an electronegative atom come together. Electropositive is just opposite of electronegative. So if I go ahead and open up a new window, I'm going to go to p-table, and there is a box somewhere where we want to see our electronegativities. So here's our electronegativities. This one has a color scale, it has a linear scale, it has a logarithmic scale. That just helps you kind of see maybe a little bit better. It doesn't matter which one you use, just which one you like the best. We talked already about sodium chloride. Chlorine is right here. The electronegativity is on here. It might be kind of small to see. I'm not sure, depending on the size of the video that you're watching. It has a electronegativity of 3.16, and when we bond it to sodium, sodium has an electronegativity of 0.93. Those are vastly different, and so chlorine is going to try to pull the electrons very strongly, and sodium is going to allow that to happen because it doesn't want to pull it necessarily as strong. And so we say that that electron, this sodium electron, has been pulled closer to this chlorine. This chlorine's kind of taken it away. And so this isn't necessarily a, there's some equations and stuff that you can use. What I've done here is I've just said, if you take the two electronegativities and take the absolute value of them, so we don't necessarily have to worry about order here, we can kind of see the difference between these. And the difference between sodium and chlorine is larger than 2. We can assume that this forms a strong ionic bond. What we want to do is we want to look at the electronic shell structure of each of these so that we can better understand it. And so I have sodium here. Let me move this slightly. We have sodium, and the electronic shell structure, the electron structure of sodium, is the exact same thing as neon plus one more electron. And so we have sodium, which is here on row 3, and we're saying that it has the same electron structure as neon. That last one here on row 2, our element number 10, and sodium is number 11. And so what we've done is we have one more electron. Neon has a full, complete valence shell, and so if I add one more electron to it, I have to start a new shell. And so this sodium just has one extra electron compared to neon, and it is in the 3s shell. And there's only one electron. That's what this 1 means here. So really, for this to become a stable electron, not a stable electron, a stable atom, what it really wants is it wants one less electron. To be stable, we want some type of noble gas electron structure. It wants to have that full valence shell. There's 2 ways to do that. Gain more electrons so that this new shell that we've started gets full, or we can take electrons away so that we just have this full shell of the neon. Since there's only one electron here, it's easier to take one electron away than try to add a whole bunch to it. Chlorine, on the other hand, has the electron valence structure of neon, plus we have some more electrons. And so again, going to the periodic table. We have neon here. That's the last time that we had a full valence shell. We added 1 electron. We add 2, 3, 4, 5, 6, and 7. So this has 7 more electrons, and we only need 1 more to get to the next noble gas electron structure. So it has 2 electrons in the 3s orbital. It's 2 electrons. And in the 3p orbital, it has 5. It only needs 1 more to fill up the p orbital here. And then it can look like argon, and then it would be stable. So if we go to this sodium and we take 1 electron away, we actually end up with an ion. It becomes positively charged. We take 1 electron away. Now it has 1 extra positive charge compared to the negative electron. We get the Na plus ion. And here with the chlorine, if I add 1 more negative charge, if I add an electron, it gets a little bit more negative, which means that we get Cl negative. Now what we have is we have something that's positively charged and something that's negatively charged, and we can see that those are eventually going to want to come together. All right, so here we have electron transfer. And if we have electron transfer, it means that we're having some type of chemical reaction, and we do this to achieve a full valence shell occupancy. So what happens, the result of this is we get something that's electronically stable. We have something that is in the form of a noble gas electron structure, so that electrons are nice, the entire shell is full. That means that those ions aren't going to be reactive. And what we end up with is we have charged atoms, which we call ions. These ions are we're going to say that they're free to move. If they weren't free to move, they'd be locked. But what we want to do is we want to say, okay, so if I have these ions and they're free to move, that means I can start arranging them in space somehow. There's going to have to be some periodic spacing of these ions when I make a ionic solid, often called a ceramic. So if I have a whole bunch of ions come together, we call it an ionic solid, also called a ceramic, and they're held together by these charges. What we have here is we have a picture. And if I have a positive charge, such as Na plus, and a negative charge, such as Cl minus, they're going to attract each other. And they're going to be omnidirectional. It means that there's not necessarily going to have to be a specific angles that these happen at. It's just pulling in from all directions. We can think of this like gravity. This positive charge is going to be pulled closer by this negative charge and vice versa. And it doesn't matter which direction, they're just going to be pulled together. We're also going to say that these are unsaturated. And what unsaturated means is it means that I can keep pulling in a whole bunch of these positive charges around this negative, and it's not like, oh, well, we already have a positive, we don't need you anymore. It's willing to keep pulling as many positive charges around it as needed. We're not necessarily going to pull, 100 of them around it, and the reason for that is if I have a solid, I'm also going to need to have more of our negative charge come in here. And so our negative charges are going to end up sitting in between here. Let me see if I can get this drawing real quick. So if we get more chlorine sitting here, chlorine ions, then maybe I will get, maybe I would get a more of my sodiums. And eventually what happens is we end up having this large thing happen. This aggregate of ions becomes a solid. We need lots of these so that we can actually have a material. And so we have to have some type of spacing between them, some type of periodic spacing. So we have are negative charge surrounded by positive. But then there are going to have to be some negative charges so that I can have some more positive charges, and we kind of grow these out. So there's going to be a little bit of math that we have to do here to really understand what's happening. And we'll talk about it briefly, but just like we've done in some past videos, what I'm going to do is I'm going to go through this somewhat quickly. I'm not necessarily going to talk about it super in depth. What I want you to do is I want you to take the time to think about it and try to understand it. This is very important stuff. We're going to talk about this picture a lot throughout the rest of the quarter. It has to do with a lot of the properties that we'll discuss later. And so I'll give you a few definitions. We have Fa, and that's going to be our attractive force. And what we really need to understand that from a distance, ions just look like simple positive and negative charges. From a distance, we say, oh, that sodium is positively charged, and from a distance, that chlorine is negatively charged. We have Fr, which is the repulsive force. What happens is as they come closer together, as we look a little bit more closer at that sodium, yeah, it's positively charged, but it's actually made up of positive and negative charges. It just so happens that it has more positives than negatives, but there are definitely some negatives there. Same thing with our chlorine. When we look at it, it looks negatively charged, but as we bring it closer, it has some positive charges as well. And so things aren't going to necessarily just be as simple as saying simple positive, simple negative. So what we want to look at is we want to try to find our equilibrium. We say that our Fn, our net force, is going to be equal to our two other forces added together, our attraction plus our repulsive force. And all that means is it's our net. We sum those together. At equilibrium, we say that our net force is 0. If you've taken some statics before, think of this as a statics problem. I have two forces acting on something, and when I don't have any movement, when I don't want things to move, I can set those equal to 0, and I can look at how those two forces interact with each other. All right, so now we're going to talk a little bit about some calculus, a little bit of physics, and we're going to say that our energy is equal to our force through a distance. And I'm going to call our distance r because that's going to be kind of our radius between these ions. It's going to be our distance between them. And so simply, we could look at that and say, even in when you haven't done calculus in physics, we could say that energy equals F times some distance. In this case, our distance we're just calling r. And so what we can do is we can do a little bit of math here, and what I've done is I've said, all right, well, if this is true, we can sum our energies, our attractive and repulsive energies together to get our net energy. I can integrate that through the distance. Those things are apart, our two charges are apart from each other. And what that does is we end up with these equations here. So what I want to do is I want to try to graph these, and to be honest, I really debated on doing this really nice or finding somebody else who had already graphed these really well so that I could show you, what they really look like. But I think building them together and talking about them could be very beneficial. And so what I'm going to do is I'm going to try to do this as good as I can. There are going to probably not line up perfectly. But what I'm going to do is I'm going to say, all right, here's our picture. And this first one, we're going to do two of them. This first one is our force. And so this force, what we're going to do is we're going to say as our atom, I have one atom right here at our origin, and I'm going to say that this is our positive charge. And then I have our negative charge over here somewhere on our radius. And as these come together, they're going to be attracted more and more. Again, you can think of this kind of like gravity. So I'm going to take this and I'm going to say that our attractive force is going to look something like this. So then what I'm going to do is I'm going to get a different color here. Let's do blue. And I'm going to put our repulsive force on here. And as it gets closer and closer, it's going to repel more and more. It's going to give us a negative force. And as I move, it's actually not going to repel very much because, again, from a distance, they just look like simple positive and negative charges. But as it gets closer and closer, it's going to drop down. And so this is our repulsive force. And it actually drops down very quickly as it gets close together. Now what we want to do is we want to look at our net force here. And so we're going to sum these together. And all we're going to do to sum these together is I'm going to take every single point at R, I'm going to sum these two together, and I'm going to put a new point in here, and we're going to see what happens. And we're going to end up with something that looks kind of like this. It's going to be in between, but slightly positive. Something maybe along these lines here. All right, so I have our net force. Now what we're looking at for equilibrium is we're looking at the point where our net force equals 0. That was this portion right here. So our net force equals 0 right at that spot there. I'll make a nice big dot there. So that's going to be a very, very important part. And what I'm going to do, because I know where I'm going with this, is I'm actually going to make a dotted line all the way down into our next graph. So what we do is we would look at this next section here, where we would say, all right, well, to turn this into an energy, we would integrate it through our distance. And what I want to do is I want to put our curves on there again. I'm going to use my green again for my attraction, but when I integrate it, it's actually going to flip it into the negatives. And so my attractive energy is going to end up doing something like this. My attractive energy. When I do the same thing for my repulsive energy, it's going to again flip. It's going to become positive. And it's going to do something along these lines. My energy repulsive, my repulsive energy. And now I'm going to sum these together again. And again, to sum them together, what I do is I take whatever value is here and the value is here. I'm going to add them together. One's positive, one's negative. They're going to end up somewhere between them. And in this case, let's see if I can do this correctly, make it look at least as accurate as possible. I'm going to end up with something like that. And this is my my net energy. And this hopefully makes sense if we take a look at it. So now we're going to take a look at it for just a second. We have this spot here where our net force is 0. That's at equilibrium. And at equilibrium, when nothing wants to move, when everything's happy, and we're at equal, our equilibrium forces are all at 0, we should assume that we're going to be at a minimum in energy, right? Because energy wants to kind of sit at that middle point. When these two atoms come together, eventually we don't want them too close together. We don't want them too far apart. We want them to sit where they naturally want to be, and that natural state is going to be at its lowest energy point. And so that's why I put this dotted line here. This spot down here is going to be our minimum energy. Often, what I'm going to write or is called our E naught, our kind of our starting energy, our baseline energy. And this point here, where we cross our x-axis, our R, is going to be our R naught. it's going to be our radius at our minimum energy, and it's going to also be our radius when our equilibrium forces are at 0. We'll talk more about this in class. It's very, very important. I do want you to spend some time looking at this. It's a little bit sloppy. There are some nice online pictures of it. Maybe I'll post one up so you guys can look at it. But drawing it out is helpful. So I wanted to draw that out with you guys. But what we have is, again, we have a positive and a negative charge, and when they come together, the attraction gets better, but also the repulsion gets stronger, and eventually we're going to get this midpoint where equilibrium happens. And what we're going to do is we can look at the same thing but on an energy scale, and as things get closer and closer together, our energy goes down as far as attractiveness goes. But as they get closer and closer together, we're going to have to put in energy because they're going to want to repel each other. And so there's going to be a spot where everything is at a minimum energy, and that is going to be at R0. All right, so let's talk about a few things really quickly. What is EA, our attractive energy? We can look at it as the Coulombic potential. And so from physics, we get something like this, where we have our negative Q1, Q2, those are our charges. And so we have this over here to show us kind of what our charges are, over 4 pi epsilon naught R. What I can do is I can simplify some things. We love to simplify things in math. We want things to look simple. This isn't necessarily difficult, but we want it to look more simple, more clean. And so what we can do is we can make it look much more simple and clean. We can just have it be negative A over R. And in that case, A equals everything else besides the R. And so we can simplify things quite a bit by looking at it this way. ER, our repulsive energy, is much more complicated to calculate. And so what we do is we're normally going to find it experimentally, or we can solve for it. But it's going to have the form of, and again, it's positive, not negative. It's going to have the form of B over R to the N. And N is going to be some number that's normally between 5 to 12, somewhere in there. And normally it's pretty close to the middle of that. And so we're just going to say that often it can be 8. The next type of bonding that I want to discuss is covalent bonding. And covalent bonding a lot of time is called electron sharing, or it's described that way. And again, it's between atoms with high electronegativity. So both of them have to have high electronegativities. If we go back to the periodic table, what we see here is the ones with the high electronegativities are kind of up in this upper right-hand corner here. Remember, there was that stair step on that periodic table I showed earlier. Right through here, this diagonal line here is kind of the cutoff between our metals, which are to the left and down, and our nonmetals, which are to the right and up. When nonmetals bond with other nonmetals, they tend to bond in covalent forms. And you'll see that these are our higher electronegativities. We got fluorine at almost 4, and we got carbon at over 2.5, and nitrogen and sulfur. And so these are larger electronegativities, which means they want atoms, or sorry, they want electrons. They don't want to give up their electrons, and they would also like somebody else's electrons. So when multiple things come together, when 2 oxygens come together, they want the other oxygen's electrons, but they also don't want to give up any of theirs. And so what they do is they share them so that they all have enough electrons. So covalent bonding, possibly in your chemistry, you did Lewis dot structures. We're going to talk about these briefly and do a few of them. Let's see, come on, pull that down. All right, here we go. I'm going to draw in our dots. I'm going to start with the red ones. I have a red hydrogen here, and so it's going to have a red electron. And we have a blue hydrogen, and it's going to have a blue electron. Now the idea here is each hydrogen, for it to be stable, wants to have a full valence shell. It wants to have the electronic structure of a noble gas. The noble gas that's closest to hydrogen is going to be helium. And so what we want to do is we want the electronic structure of each hydrogen by itself to be looking like helium. Helium has 2 electrons. When these come together, we have hydrogen now having 2 electrons. It has its own electron, plus it's sharing or borrowing the other hydrogen's electron. And so we can say that this now has the electronic structure of helium. And so everything's good. It's stable, it's happy, it has a full shell. Well, the other hydrogen has its own electrons still, and it has the other hydrogen, the red hydrogen's electron. So it has the electronic structure of helium. And so now it's stable. Both of them are stable, both of them are happy, it's bonded. This is a covalent bond. They share electrons, and in this case, they saturate. We said previously in the Ionic bonds that you could kind of have as many things around it as possible. In this case, it's a 1-to-1 because they're sharing. Once an electron is shared, it can't be shared anywhere else. It's kind of stuck with the atom that it's decided to share with. We could do nitrogen. Nitrogen forms a triple bond. And so I'm going to put 3 electrons for my red one there. Those form the triple bond. Nitrogen has 5 valence electrons, so there's 2 more we'll put on this side. And the other nitrogen has the exact same thing. 3 electrons that are going to bond with the triple bond, and then 2 that are not involved in the bond. Now, nitrogen, it's 1 step lower into the periodic table. The first layer of the periodic table, the first row, that with hydrogen and helium, you can only have a maximum of 2 electrons in that shell. For all the rest of them, we talk about having that octet stability. They need 8 electrons to fill that last shell. And so that's what I have here. I have these 6, which they're sharing in the middle, and then the 2 on the outside. So we have 6 plus 2, that's 8. So this red nitrogen has 8 electrons, and it is going to have the structure of neon. I looked that up earlier, so I hope that I wrote it down correctly in my notes. What I'm going to look at real quick to double check is we'll go to the periodic table. We have nitrogen, and if nitrogen gets 3 more electrons, 1, 2, 3, then yes, it does have the electronic structure of neon. And since it's in this last column here, it is stable, it has a noble gas electronic configuration, and we are happy. Now the other nitrogen, the blue nitrogen, has the same thing. It has the shared electrons in the middle, so there's the 6 here in the middle, and then the 2 that are not used in bonding. And so this one also has a neon electronic structure. So what we have here is we have our non-bonding electrons, and here we have our bonding ones. And again, sorry for my handwriting. And these non-bonding ones, those are our orbitals or our domains, our bonding domains, and which we'll get into just slightly. Again, you've had it in chemistry before. That is a prerequisite for the course. And so this is more of kind of a quick review of the subject. All right, Before we get too much further, I want to talk about hybridization theory. And what hybridization theory does is it mixes our s and our p states, or our s and our p orbitals, to maximize the number of bonds and to minimize energy. Remember, if we scroll back up to the very top, everything comes back to energy. And what we want to do is we want to talk about energy. We talked about energy when we were discussing our ionic bonds, right? We had our minimum energy here. We are talking about energy again here. So I do want to scroll back up really quickly just to when we were talking about our sodium and our chlorine. And our sodium had a 1 electron in an s orbital, and chlorine had an s orbital that had 2 electrons, and it had a p orbital that had 5 electrons. So hopefully you remember a little bit about s and p orbitals. Here is our periodic table. This column has 2 elements in it, 2 atoms in it. And so a lot of times we think of this as these are our s's. So the first electron fits into our s orbital. The second electron fits into our s orbital. 2 electrons per orbital, one with spin up, one with spin down. We look over here and there are 6 more over here. We're kind of ignoring our metals for now. And so we're looking over here, there are 6 elements or atoms here. And those 6 we would consider being primarily our p orbitals. And so there are 6 electrons in our p orbitals. That means we have 3 p orbitals, each with 2 electrons, 1 spin up and 1 spin down. All right, so the idea here is, if I have these different orbitals, the orbitals are the things that bond. And we showed that briefly here, where I have my bonding happening, and these are our overlapping orbitals. If I wanted to look at something like, let's say carbon, or nitrogen, or something on this line here, this row 2, we would be talking about our 2s and our 2p orbitals. So here's my energy. I have an energy diagram here where energy is increasing as I get higher up on the screen. And normally what I have is I have something like this where I have a 2s, and then at a slightly higher energy, I have my 2p's, and these p's sometimes are referred to as my x, my y, and my z. Now again, each of these can hold 2 electrons, 1 spin up and 1 spin down. The problem with this is if I have something like carbon, and if carbon wants to bond with hydrogen, so here's our example down here, carbon wants to bond with hydrogen, we end up with something that looks like this. We have carbon, we have 4 hydrogens around it. And this doesn't necessarily look like it's symmetric. It should be symmetric. The idea here is maybe these ones here are actually coming out of the screen. And maybe they're going into the screen, and this one's coming out of the screen. And so I'm going to make it look a little bit different. It forms kind of like a tripod. The hydrogen on the top's sitting, let's say, straight up, right above the carbon. The hydrogen at the bottom is coming out towards us, and the hydrogens on the left and the right are going behind the carbon and to the side, so it forms kind of a base. And all of these are going to have an angle of 109 degrees about. It's about 109 degrees. And it doesn't matter which one. The angles between these two are going to be about 109 degrees, and the angles between these are 109 degrees. The angles between this hydrogen on the bottom and the hydrogen up top is going to be about 109 degrees. Now, if we had bonding happening, like we have above right here, we wouldn't get this picture, because one of our bonds would be in a 2s orbital, which is at a lower energy. So it would bond differently than our other 3 bonds, our 2px, 2py, and our 2pz. Those would bond differently. We would end up with something, it might look similar on a piece of paper or on a screen, but it would actually look something like this in real life as well. They wouldn't be symmetrical. This would be, let's say, larger than 109, and these ones would be all smaller than 109. Because there'd be unequal energy, one hydrogen would bond more tightly than the rest of them. And so to make a symmetrical molecule, we need to have something else go on here. And again, if we want to minimize energy, things that are symmetrical tend to be at a minimum energy. And so we want to do that, and it wants to happen. So what's happening here is we have hybridization. And what we can do is we could raise up this 2s's energy a little bit, but in doing so, we could reduce the p's energy. And we could put them all on one line. And what we would do is we would call this our 2sp3. And that 3, again, is just the notation because we have 3 p's. I could put the 3 here, saying that we have a 2s and we have 3 2p orbitals. I could look at 1 and say, well, what if I only wanted to bring 3 of those levels down? Well, I could have a 2sp2, and then I could have my last 2p, or I could bring maybe just 2 of them down. And I could have a 2sp, and then my last 2 p's up here, 2p2. And then what I do is I can fill in my electrons. If I look real quick at our periodic table again, here's carbon. And so if I start all the way over here at lithium, there's 1 electron, 2 electrons, 3 electrons, and 4 electrons. 4 electrons above that of helium. So there's 4 electrons I need to put inside of this diagram here. All right, so what I can do is I can take this, and normally what we do, electrons want to sit at the lowest possible level. And so 1 electron would sit here, spin up, 1 would sit here, spin down, and I'd have 2 more. Well, in this case, I only have room to bond 2 things, because to bond, I need 1 electron in any given orbital so that it can grab another electron and they can share, they can bond together. In this case, I could only have 2 bonds. It wouldn't be this molecule down here, methane, it wouldn't be CH4. Well, I could do the same thing with all of these. Let's start on the right-hand side. If I fill in my 4 electrons, spin up, spin down, spin up, spin down, there are no lone pairs. There's nothing left to bond. I could do the same thing with this one. I'm going to fill them all up with the one that's spin up. I have 1 more left over. I drop it down here. Again, I only have 2 spots where I can bond something. And I have this last picture here where I could put 1 in each of these. And what that does is it gives me 4 equivalent bonds or possible bonds that can happen. And so this is how we end up with this molecule. And what's happening here is it just happens naturally. It reduces energy. It's at a lower energy state. And so it's happy to do so. Again, we'll talk about this in class. You got questions, let me know. Write some things down. Think about it for a bit. Maybe pull out your old chemistry textbook. Pull out the material science one. They're probably talking about something along these lines as well. I wanted to jump quickly into our pi and sigma bonds, or sigma and pi bonds, and those are just the bond types. So our sigma bonds are going to be our really tight bonds. If I have an atom and I want to bond it to another atom, I want to have those things meet up together, I want to add those two together, what I do is I take the orbital. And in this case, we're going to be looking at an orbital, a p orbital or something that looks like this. You've probably seen pictures in a textbook where you kind of have these lobes off of each side. Those are my probabilities of where I'm going to find my electrons. I'm going to find my electrons somewhere inside those lobes. If I want to add the two together, if I want them to share that each other's electrons so they're bonded together, what I'm going to get is I'm going to get, and I'm going to write it over here, I kind of ran out of room. They're going to come together. So as I move these two closer together, I'm looking at my picture on the right-hand side. As I move them closer together, this picture and this picture, those two lobes are going to kind of meld together into one big lobe. And that is a bond because the electrons that are sitting in these orbitals, and the electrons could be over here as well, they overlap. And that's what we get here. We get this overlapping. And so we get a bond, and we call this our sigma bond. And what a sigma bond means is it means there's no nodes between the atom. There's no broken electron density. In other words, if I go from one atom to the other, I got a straight shot between them, and I have this big electron cloud, this spot where my electron can be, directly between those two atoms. If I want to look at my pi bonds are different. They're when I have a second bond or a third bond. And so I already have this sigma bond taken care of. And if I want to bond, have a double bond or possibly a triple bond, what I'm going to do is I'm going to say, all right, well, I have this additional bond. I have the lobes that go up and down. So these lobes would be like my y-axis. Sorry, my x-axis. These ones would be my y-axis. And that's what we see when we're looking at these p bonds here. I have some that are my x, some in my y, some that are in my z direction. So let's say my pi bond is in my x-axis. My y-axis also has electrons that would like to bond. And so I'm going to add these together, and as they get closer and closer together, they're going to overlap. This lobe up here at the top, let me shade it in a bit. This lobe up here at the top is going to want to overlap with that lobe, and this lobe at the bottom is going to want to overlap with that lobe. It's going to create a bond, and they have to overlap for that bond to happen. And so what we end up having is these come together, and remember that sigma bond is already there, and I'm not going to necessarily draw it in, but this at the top, these two are going to overlap, and they're going to kind of stretch over each other. And the reason it has to stretch over is because, again, there's that sigma bond in between them, and so they can't just go straight across. They have to kind of reach over and around that sigma bond. And the lobes at the bottom will do the same thing. This is a pi bond. And a pi bond is a secondary or a third bond, a second or a third bond, but there is broken electron density and there is a node. And what I mean by that is if I were to draw a dotted line where my sigma bond is at, in between these two atoms, it has to go up and around. My electrons have to go up and around. There's a gap between these two atoms where the electrons can't be. And so that's what a pi bond is. It's something that reaches around. There is going to be a gap between my two atoms and the electrons. One thing that I want to mention is there is a second pi bond that's possible if we wanted a triple bond, such as when nitrogen bonds with itself. And that second pi bond would be in a z-axis. And in this case, if our x-axis is moving left to right and our y-axis is up and down, our z-axis would be coming in and out of the screen. And so it would be doing the same reaching up and around, but it would be coming out of the screen to reach around to the other atom. And then there would be the bottom lobe, the second lobe, that would be reaching into the screen and around to the other atom. So hopefully that makes sense. But it's just the way that the bonds happen, the orbitals happen. And why is this important? Because if we're really talking about how a material works, when our atoms come together and we have these electrons, and when the electrons come together, if it has something to do with energy, then that means things are going to act a certain way. And when they are bonded a certain way and they act a certain way, then we get specific properties. And so that's why it's important. And again, when we get closer to talking about properties, we'll review this and we'll use it more in context. Right now, we're talking more review than anything else. All right, so quick review for a covalent bond. They share electrons, so there can only be a certain number of bonds. They do saturate, and they're very, very directional, and they're dependent on the electron shell. All right, this one's going to be a quick one. Metallic bonding. Metallic bonding is often called a sea of electrons. It's between atoms with mid to low electronegativity. These atoms have loosely held or loosely bound valence electrons, and there are some types of materials we could think about. They're loosely bound because maybe they only have 1 or 2 valence electrons, or maybe they have d orbitals, and so there are some things going on here. We have some examples. They could be pure metals, or we could have alloys, and alloys are mixtures of different types of metals. So to keep things simple, we could say that we have sodium, and sodium is a metal, and it just has that 1 extra electron. For it to have a complete electron shell, it needs to do one of 2 things. It either needs to lose 1 electron, or it needs to borrow a whole bunch of electrons from somebody else, from some other place. So what we're going to do is we're going to look and see what's going to happen here. I made this a little bit too long. Holy moly. Should have double checked that before I came onto here. Let's see, I'm just going to read it so that I don't have to necessarily change it. Neon by itself has a lower overall energy. It's stable. So when sodium comes together with another sodium atom, or with other sodium atoms, the extra electron, the 3s1, dislocates and distributes throughout the solid. Thus, it's a sea of electrons. Without the loosely bound valence electron, the ion that is left is held together with the delocalized electrons, and it really doesn't care which electrons are theirs as long as there's the proper number of them nearby. All right, that's a lot of words. Let's draw a picture. Pictures are much, much better. All right, so here is my material. And what I have is, let's say that this is sodium. I'm going to draw in these circles, and these circles are not sodium atoms. What these circles are is they're sodium atoms without that extra electron. So it's kind of those core electrons, the electrons that already have this this complete shell within it. And so inside of here we have our protons, we have our neutrons, and we have all of our completed shells, completed from wherever else they might have come. In this case, sodium here is on row 3. And so it has a full shell that looks like neon, and it has a full shell of electrons that look like helium, and we're incorporating those inside of here. All those electrons, the ones that completed a full shell, are all inside of here. they aren't going to react anymore because they're all happy because they all have completed electron shells that look like a noble gas. What that means is each one of these sodiums come with that extra electron. And so if I have 6 atoms in here, that means I need to have 6 electrons, 1 for each of those. The idea here is because they're so loosely bound, they don't necessarily care which electron, extra electron they have, as long as there is an extra electron nearby. They're perfectly happy having whatever nearby electron that is. So in this case, we could say, well, if I draw a circle, this is a sodium atom because it has the core of a sodium atom plus 1 more valence electron. And I could look at that with all of them. But I could look at it and instead say, well, what about this? It has its extra electron. It's perfectly okay with it. And if that's the case, then maybe this one would be looking at that one, and maybe this one is grabbing that one. And as long as they are all grabbing something, then they're going to be okay because they all have 1 extra electron that they're considering their own, but it's loosely bound and they don't really care which electron it is. Now I exaggerated here, they're going to want the one that's closest to them. But this is one reason why metals are considered conductors. And again, we'll get into this when we get into properties, but if they don't care which electron it is, I can pop an extra electron. Let me get rid of some of these. I could pop an extra electron into this side here, and now there's 1 too many electron, which means that all these are happy and there's 1 extra electron. Maybe one of these electrons is going to have to move away. And that's how we get current. Again, it's a bad picture, but the idea is there. You can think about it for a while. We'll get into it probably in a month or so when we get through all of our theory and we start talking about our properties. And so it's an interesting way to start seeing what's happening and the differences between the different types of bonds. So we have ionic bonds, where we pretty much say that an electron literally moves to a different atom, moves away from one and into another, electron transfer. We have covalent, where 2 of them are unwilling to give something up, so they share. And then we have then we have metallic bonding, where as long as there is the right number of electrons around them, they don't care where those electrons come from. They're loosely bound and they're perfectly okay to come and go and change as needed. Now, one quick thing, let's say that oxygen comes along, and oxygen has a much different and a higher electronegativity. And so sodium has a low, oxygen has a high, and if we scroll back up, we look at some of these things in here, and for ionic bonding, if I have a spot where I have atoms with large differences in electronegativity, I get an ionic bond. So oxygen comes along and it's very electronegative, which means, here's my oxygen, big O for oxygen, it wants some of these atoms, or sorry, some of these electrons. It's going to bond into here and it's going to pull these electrons closer towards it. That's what happens when a material oxidizes or when iron rusts. The idea is the metal is inside the material, and on the surface where we see that oxidation is actually a thin ceramic layer, a thin ionic layer, because it is between a metal and something that is highly electronegative. So again, something to think about in the future when we start talking about properties or how things matter, or when we talk about reaction properties, chemical properties. All right, so really quick before we get to secondary bonds, in reality, all materials are made up of mixed bonds. And what that really is talking about is it's saying that, well, first off, an electron truly doesn't transfer for ionic bonds. It just gets really, really close to one of the atoms compared to the other. And for covalent bonds, do they actually get shared equally? Usually not. One of them still wants that electron a little bit more than the others, and so it kind of looks like ionic because it's still pulling it a little bit closer and closer together. And so what we do is we call this ionic character. We want to see how much character this bond has that's ionic compared to how much that it has that's covalent. There is an equation, there's a few equations that I've seen out there where you can calculate the percent ionic character, and the opposite of percent ionic character would be the percent covalent character. How much does it act like an ionic bond compared to how much does it act like a covalent bond? And so I have a picture here, carbon monoxide. And this is the picture that we draw in chemistry. And we say, hey, there's a triple bond here. Oxygen comes in with 5. Carbon comes in, 2, 3, 4, 5, 6. Carbon comes in with 4. And we get this triple bond. And everything's happy. And everything works. And we call it covalent. That's wonderful. When in reality, it is true that we consider it a covalent bond. But it looks more like this. The oxygen is more electronegative, which means that it's going to pull even those shared electrons just slightly closer to it, acting almost like an ionic bond. Even if it happens ever so slightly, it isn't necessarily 100% shared equally. And so we would say that this is still a covalent bond because it is more covalent than ionic. So there are going to be some homework problems on that. We might also do some problems in class. We'll talk about maybe that equation, but it's an easy enough equation to find. It's a good habit to where when you are giving a problem, you're not sure what to do. I mentioned that there is an equation that can calculate the percent ionic character. Go ahead and look it up. It's in the book. It's in a lot of places, and so when we come to that problem, I'm not necessarily just going to give you that equation. It's an easy enough one for you to find. I want to finish up really quick talking about secondary bonds. And secondary bonds are our van der Waals bonds, and what they do is they are when non-charged atoms and molecules condense, and they're held together by other types of bonds. And when I say non-charged atoms, again, they're going to be atoms that are already considered stable, or molecules that are considered stable. They're not ions. They don't want more or less electrons. They're already happy with the number of electrons that they have. So these bonds do not include electron sharing or transfer. The bond strength is going to be weaker normally for these compared to the primary bonds, and the melting point is normally lower as well. The melting point normally is consistent with the strength of the bonds. There are 4 types. We have hydrogen bonds, sometimes called H bonds. Those are the strongest of these secondary bonds. We have dipole-dipole, dipole-induced dipole, and then induced dipole-induced dipole. And we'll talk a little bit more about those as we move on. But I do have this picture here of kind of how they go. They go from strong to weak. All right, so hydrogen bonding. Hydrogen bonding is when hydrogen is bonded to a highly electronegative atom. We really basically say that that works for nitrogen, oxygen, and fluorine. We don't consider chlorine to make an H bond, a hydrogen bond, due to the fact that the valence electrons are too far away from the nucleus. And so they're very, very specific. Some examples: water, DNA, amino acids, some polymers that we have. I have, there we go. The idea here is we have a partial positive part of a molecule and it will be attracted to a partially negative part of a molecule. It's similar to ionic bonding, but there's no electron transfer. So here's my example. Here's water. We're going to have water. I have oxygen. I'm going to have oxygen be a big blue circle, and I'm going to have hydrogen. Hydrogen, I'm going to have small red circles. And these are bonded together, and the molecule is happy. It's stable. It's not the fact of there's extra electrons somewhere that really want to react somewhere. We have to look around and see what's happening. There are some additional things going on here. We have some lone pairs of electrons out here that aren't bonded to anything. But again, they're okay not being bonded because there's two of them there, and so it's stable. They're fine. They're just happy being two lone electrons. What we have, though, is we have a dipole. We have the fact that one side of this, my hydrogen, is more positive. That's a lowercase delta with a plus sign. It's partially positive. That's what we use delta for, meaning partially. This hydrogen here is partially positive. And my lone electrons up here and my oxygen are going to be partially negative. And so even though it's a stable molecule, part of my molecule is a little bit more positive than another part of my molecule. As I reduce thermal energy, as I take heat out of it and they stop rotating and vibrating so much, what's going to happen is they're going to get closer and closer to other water molecules. And so I'm going to get an oxygen over here, which is bonded to two hydrogens. Oops. All right, there's that. It has its lone pair of electrons. And this oxygen also has an area that is partially negative and some areas that are partially positive. Well, the positive parts are going to be attracted to the negative parts of the other one. So right here, I have this partially positive part of one of them, the hydrogen, and it's going to be attracted to the partially negative part of the other water molecule. And if you take enough thermal energy out of there, they're actually going to want to stay kind of stuck together. There is no electron transfer here. They're just the fact that I have something positive and something negative coming close together, they're going to want to attract. So that's a hydrogen bond. A dipole-dipole is actually the exact same thing. A hydrogen bond is a dipole-dipole bond. We do see that we have one molecule that's a dipole, and we have another molecule that has a dipole, or a polar molecule and a polar molecule, and they come together. So what's the difference between hydrogen bonding and dipole-dipole? Well, if we have a dipole that is between hydrogen and nitrogen, oxygen, or fluorine, it is just so much stronger than other types of dipole bonds that we give it its own name, just because it's so much significantly stronger than the other ones. But a dipole-dipole is exactly the same thing. It is a just interaction, but not between hydrogen with nitrogen, oxygen, and fluorine. So we have something like HCl or polymers. And so here we'll just do a quick example. We'll do HCl. Here's my hydrogen. Here is my chlorine. Instead of doing different colors, I'm going to do one is large, one is small, and my hydrogen I'm just going to fill in as well. One side of these is partially positive, and one side is partially negative. And as it gets close to other molecules, this molecule is partially positive and partially negative. And again, this negative side and this positive side are going to be attracted. And when we take enough thermal energy out, they're going to stick together. All right, we have dipole-induced dipole. What this means is this one was dipole-dipole, and what that means is I have one dipole bonded with another dipole. So if I say I have a dipole-induced dipole, I have one molecule that has a dipole. It has a side that is partially positive and a part that is partially negative. I just noticed that I put an X there, I guess. Oh, no, we're good. All right, so one that actually has a dipole to begin with, and then one that doesn't. And so I could take my water molecule. I have my water, partially positive side here, and I have my partially negative side here. And that's going to get close to, let's say, something like methane. And methane was carbon. I'm going to put a C in here so we know that that's carbon. And carbon has hydrogens around it. And carbon overall, or not carbon, methane overall isn't really that polar because it has hydrogens all the way around it, not just on one side of it. It is true that the inner side of my my molecule near the carbon, it's going to have a different electronegativity than the hydrogens on the outside, but these outside ones are all the same. But as I have this electron cloud around it, and so what I'm going to do is I'm going to draw these little dots around it, and these dots are going to be kind of my electron cloud, the orbitals where the electrons can be. As it gets closer and closer to this polarized molecule over here, something very interesting is going to happen. Let me take a few of these away. This is partially negative, right, on my my water molecule, which means as it gets closer and closer, these negatives that were near it are going to want to shift to the opposite side. Well, now I have a polar molecule. It's not very polar, but one side, this side, is more positive because the electrons have kind of been pushed to this other side. So the electron cloud shifts away from something that is negatively charged. And as, again, we take away thermal energy, it's going to get close enough together to where it is going to stick. Lastly, we have induced dipole. A molecule or atom without a dipole has constant shifting electron cloud around it. The electrons are always moving, the cloud is always shifting. As the cloud shifts, there is a small dipole that is formed, and it's instantaneous. It's there and then it's gone, or it's there and then it's somewhere else. But if this happens near another molecular atom that is not a dipole, what it can do is it can kind of induce that nearby molecular atom to have its electron cloud shift as well. Due to thermal energy, this usually has very little impact until we either get super, super, super cold or until we have a huge number of these bonds. And so here we have something like neon. Neon is a noble gas. It's not going to want to bond together. So I have neon, it's happy, it's got its electron shell around it. It doesn't want to transfer any electrons at all under any circumstance. I have another neon that's in the same boat. But as we push these together, as these electron clouds somewhat start shifting, what's going to happen here is, I'll draw a new picture here. This neon, let's say, gets an instantaneous dipole. A little bit more negative charge ends up on one side of the atom than on the other. Well, if it's close to the other one, what it's going to do is it's going to shift the other one's electron cloud because this negative charge here kind of pushes those other electrons away. Again, this normally only happens at super low temperatures or if we have so many things going on that it can be effective. This ends up being partially positive. This side is partially negative. This side is partially positive and this side is partially negative. Anytime we have something that's partially negative or partially positive, they're going to want to come together and be attracted, but really it needs to overcome other types of forces as well, thermal energy, the fact that it wants to vibrate, the fact that it wants to rotate, and so we need to think about our thermal energy in this picture as well. All right, so I do have a few pictures of things that I want to go through really quickly. You can take time to look at these on your own, pause them. So here's the picture that we had earlier about our electronegativity. Again, very important when it comes to bonding. Talking about the different types of bonds with some examples. Same thing with our secondary bonding, the 4 different types with some examples. And then we talk about hydrogen bonding with hybridization. We have carbon, and carbon can act very differently depending on how it's bonded, depending on how, and even within that, it's all covalently bonded, but depending on how the covalent bonds look. And so we have something like diamond, which is sp3 hybridized, and graphite, which is sp2 hybridized. I've read papers before where instead of it talking about diamond and graphite over and over and over, it just says sp3 hybridized carbon versus sp2 hybridized carbon. And, you know, you kind of have to have the background to really be able to picture what's happening. And what you might want to do is go back to your notes about the hybridization and about pi and sigma bonds and figure out why when carbon bonds with itself, in sp3 it has 4 bonds, and in sp2 hybridized, it still has 4 bonds, but one of those is a double bond. And so that might be something to look at and to think about before class. The last thing is looking at phone books. You might have heard the myth, and the Mythbusters definitely heard it, where if you interlace old phone books together, one page down, the other page down, so you have 2 phone books, and you just slowly put the pages down, kind of like you're shuffling them together. You interlock those pages. No glue, no nothing like that. The myth was you can't pull it apart. And so they tested it. They got 2 phone books, and they started pulling it apart. They tried doing it by hand. Then they got a whole bunch of people, you know, 5 people over here, 5 people here playing tug of war. They still couldn't pull it apart. You can see in this picture here, these are videos. I'm going to post this in the description, so you can go to this if you want to. They start pulling it apart with chains. They get to the point where they're pulling it apart with cars and tanks. And when it finally comes apart with the tank, it's not the fact that the actual pages slid apart. It actually ripped the spine off of the books before the pages actually slid apart. They came to the conclusion that it was due to friction. I want you to think about why it is friction or why it's not friction, or why it would be van der Waals bonding or not van der Waals bonding. That will be a good discussion for class. I will tell you that there is one answer that is correct and one answer that's incorrect, and you can use your physics and your chemistry and what we've discussed today to be able to figure out which one of those it is.